Okay, so I've got a couple of spheres that are colliding. I know the coefficient of restitution. I want to find the velocity right after impact. So the first thing I need to do is kind of determine what my line of impact is, which is going to be, this axis right here. So I'm going to call that, I'll call that my x-axis and my y-axis. Line of impact, I don't know how you want to call it, but I'm going to set things up that way because along the line of impact, two things are true. The first thing is that the momentum is conserved for the entire system because, again, that impulse, that impact force, is going to be internal to the system. If I take the system together, all of the momentums of both spheres going in there, right, in that direction. So from that, I'm going to start with that, my mass times the velocity of each one. So it's going to be 10 times 3 cosine 45. Okay, again, that's along the line of impact. Okay, and then I've got the smaller one, the 2 kilogram, going in the opposite direction, negative, and that would be times 12 cosine 30. So again, along the line of impact, those are my initial momentums. Remember that momentum is a vector. Okay, so I'm doing it line of impact and then perpendicular to the line of impact. Okay, and then what that equals is the final um, velocities along the line of impact. So it's going to be basically 10 times VA2 in the x direction. Again, I'm calling x the line of impact. Okay, plus 2VB2 in the x direction. Okay, so those are the final velocities along the line of impact, right? Because momentum is conserved for the entire system along the line of impact. Now, the other equation that I have along the line of impact is that coefficient of restitution, which is going to be just the 0.5 that I know equals VB2x minus VA2x, right? The difference in the final velocities minus the difference in the initial velocities. So that would be 3 cosine 45 minus a negative 12 cosine of 30. Okay? Now, again, two equations, two unknowns. This is along the line of impact, and I can find the velocity of A afterwards along the line of impact is going to be negative 1.01 meter per second, and the velocity of B after collision along the line of impact to be 5.25 meters per second. So along the line of impact, 2 starts going in, back, the way it came at 5. A also goes backwards, but at a much smaller velocity. Again, that's because it's more massive, harder to get it to change direction. Okay, but again, along the line of impact, conservation of momentum for the two combined, coefficient of restitution along the line of impact. I can find the velocity along the line of impact both before and after. Now, that's not all I'm trying to find. I also need to figure out what's going on perpendicular to the line of impact, okay, which is essentially my y direction. The nice thing here is there are no impulses in this direction. By definition, the line of impact is the line of the impulsive force that's happening. So what that means is my velocity just basically stays constant, right? So VAY1 equals VAY2 because there is no impulse, there is no force in that direction perpendicular to the line of impact. So it just becomes 3 sine 45, okay, which then is 2.12 meters per second. And then the same thing holds true where VBY1 is going to equal VBY2 because, again, there is no impulse, right? So the velocity just stays constant as I go through here. That's going to be negative 12 sine 30, which is just going to equal negative 6 meters per second. And again, those stay constant throughout, but both before and after because there is no impulse in that direction. So you apply conservation of momentum and coefficient of restitution along the line of impact and then recognize that the velocity remains constant perpendicular to the line of impact to find the total velocity after the impact of these two spheres.